10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Firing command. Fuel tank pressurized.
10:48 hours, Eastern Standard Time. January 31st, 1958. For another 2 hours, they would sweat it out. At the Cape, in Huntsville, and in Washington, waiting for the tiny satellite to race around the Earth and confirm the fact that Explorer 1 was in orbit.
2 months later, another 4-stage Juno I launch vehicle delivered Explorer 3 to orbit on the 26th of March in the International Geophysical Year. A little over a month later, on the 1st of May, the U.S. public received its first hint of the planet's 2 main radiation belts as a potential hazard to satellite electronics or loitering human spaceflight in the region. By 1959, these radiation belts were being explained in various magazine articles and television science programs. Both the inner and outer Van Allen belts wrap around the Earth's equator like a torus donut, with free opening out the north and south poles. The inner or lower belt, shown here in red, is dominated by high-energy protons exceeding 100 Mega Electron Volts. It ranges in altitude from 620 miles to 7,500 miles above the Earth. The outer belt is much larger and much more variable than the inner belt, and it consists of high-energy electrons captured by the Earth's magnetosphere. It ranges from 8,100 miles to 37,000 miles above the Earth's surface. I mentioned the Van Allen belts on this channel today, not so much because of the obvious anniversary date, but rather because studies with the Pamela module have confirmed that these belts are able to confine a significant flux of antiprotons generated from cosmic ray interaction with the Earth's upper atmosphere. That's right, I'm talking about antimatter. And NASA's Institute for Advanced Concepts concluded back in August 2007 that the harvesting of antiparticles concentrated in planetary magnetic fields would be feasible and could be applied to spacecraft propulsion.